Big data in memory was, as a title, it's big data for me is a buzzword. It's one of those sort of annoying buzzwords which, working in the banking environment, you tend to do a lot of the stuff. We did sort of NoSQL, and then somebody came along and called it NoSQL, and we do in-memory caching, and somebody came along and called it, grids and in-memory caching and bits. And it's one of these things that people stamp labels on, and big data is very much that as well. There's no formal definition of it. You can Google it, Wikipedia it, etc., and you get a lot of different definitions. It's a very vendor-centric thing, and all the vendors tend to put a different swing on it. My personal definition is basically something that won't fit onto one machine. So something that we were traditionally perhaps using one disk, one database, one machine. So it's really data for a grid where we're basically processing stuff that's in multiple locations. So this is where you need the map reduce, you send off your queries, aggregate the results from the queries, and etc. And how do I get into that, into memory? Well, there's a couple of things. If we're hitting disk, disk is still horribly expensive in terms of time, well, not in terms of cost, but in terms of time. If we're putting things out on the disk, querying those, getting back the results, we're going across network, we're hitting the disk, hitting the network, and it's going to go into memory in the end. And the way we used to get around this when we were on single machines, so for years and years, we were basically using caching, and caching goes into memory. And so this is something that is where I'm going, basically, is getting more and more, getting more use out of the memory. And so for the people amongst the audience that have got a few bits of grey hair or no hair at all, so those of you over about 40-ish, I'm guessing, will have some recollection of life before Java. And what we used to do, this was sort of common everyday practice, was getting the most out of the machine resources, and then Java came along and abstracted it all. So this is really trying to get the picture. It's at some point, wherever you put your data, whether it's sitting on a disk or a network, it's going to go through memory. And if it's hitting the memory or it's in memory, then obviously you want to use that and be as efficient as you can. And it's a very time-consuming process getting stuff in and out of memory. I've got some little demos here. We're going to look at the costs of serialization. We're going to look at the costs of garbage collection. And I think you're going to be pretty surprised at the sort of performance differences we can make by a few, should we say, they're relatively simple in conceptually, but it means a lot of writing code. I think you'll understand it makes a huge difference. We're not talking a few, 20, 30, 40%. We're talking several hundred to even thousands of percent in terms of difference on these. What I want to also get away with is going back to this concept of, you go back to the 90s, and the DBA was really the god. It was whatever happened in the company. It was, everything went through the DBA. The DBA knew all the salaries. All of the CFOs, CEOs, CTOs had to go through the DBA. The DBA was really just ran the company. Nothing could happen without the DBA. And then along came Java, and we started to abstract stuff, and we started to abstract the DBA. And unfortunately now the DBA, we don't even care what the database is. We get into these NoSQL or in-memory databases. We can do stuff in Java these days that outstrips anything that these DBAs could have done, even with their stored procedures and things. But with this new push with big data, we're starting to see, certainly from a Java programmer's point of view, starting to see these vendors coming back, pushing all these wonderful technologies that get back into disk and things. And I'd like to try and fight back and bring it back into the programmer's realm. So to me, the biggest problem that I see at the moment is Java, or the JVM. And I think you're going to be pretty surprised at this. For those of you that haven't got into the nitty-gritties of Java, if we take a simple string, I chose 3 letters here, ABC, because I work in financial services. Financial services, we have currencies, as you know, and they're typically 3 letters. There's actually an ISO standard. There's 163 currencies defined in that. So if we take ABC, we store that in Java. It actually takes 48 bytes. That's pretty ridiculous. If you knew you were storing a currency, it would only take 3 bytes. If you knew you were storing one of the 163 ISO currencies, it would take 1 byte. If you didn't know it was a currency, it would take 4 bytes because you'd need either a sort of size at the beginning or a null terminator at the end. But Java carefully stores it for us in 48 bytes. Now there's some other clever stuff. It uses referencing and things, so if you store the same string twice, it will reference it with another string, and then there's some sort of clever little bits that keep reference counters and things. When you serialize it, there's some other clever things that go on, but as you'll see when we run this, as we do some little tests, this very, very quickly accumulates. Now this is some simple data. It's totally fictitious, something I hope most of you will understand. I can use credit card information or something. All I'm trying to do is create fictitious information. I'm going to use this for a little test. So it's basically just, imagine these are trades, people buying and selling currencies. Now they're not the buying and selling currencies that you and I do, because they're large amounts. I've never seen, sadly, any of those amounts in my bank account. But these are sort of amounts, typical amounts that an average bank would be trading. They'd be buying and selling different currencies in different days. They would be buying one currency today, selling it 2 weeks ahead for somebody that wants to buy cars, oil, something in the future. And this is the raw information. There's lots more details to it than that, but this is the sort of raw information that they want to see. So you've got a sort of a trade ID. I'm just calling that a number. We've got a trade date, which is random days chosen in July, not weekends, a buy-sell, so you're either buying or selling, a currency, an amount, etc., an exchange rate, that's the rate that you're doing, another currency, another date, and the amount is calculated. Now, if we import that, it's typically comma delimited file, we can import that into Java. Now, let's say we wanted to work with this file. We want to manipulate it. We want to do some maths on it, do some calculations, do some processing. Now we've only got 3 lines here, but in a typical bank, we're talking hundreds of millions. We're talking billions of rows of these things. So we need to do quite a bit of processing on this. And again, remember, this is a simple version. That comma delimited file there, each one of those lines is actually represented on average by about 7.4K of XML. It's a thing called FPML, Financial Products Markup Language. So this is a very simplified version. I'm just trying to simplify it for convenience. Each line, in this particular case, is 70 bytes on average. Some a little bit longer, some a little bit less. If we put that into Java, again, on average, when I say into Java, I'm talking about using ints, doubles, dates, the usual stuff. We end up with 328 bytes for each and every single row. So we're already bloating this by about 4-fold. So if you want to put 1 million in there, that means you need 300 million or 300 megabytes just to put 1 million in there. You put in 10 million, we're into 3 gigabytes already. Now, yes, some of those strings will be referenced to other strings, etc. But also remember, this data is typically coming in on a socket. So Java's not clever enough to actually realize that when you take those strings as 3-letter characters, that they're in fact the same string as the other one. It doesn't actually compare them because that's obviously expensive. So it actually keeps each string separately. They're not referencing the same string. So you end up typically with 328 bytes, and we need 3 gigabytes to store just 10 million of them. But 100 million, that's 30 gigabytes, and you're very quickly into the realms of limits of your machine. And don't forget, that's just raw storage. If you're actually processing these, bringing them in on the network, calculating them, parsing them, serializing them, etc., you're creating a lot of garbage on top of that. So there's an awful lot of extra work that needs to be done. So it's not just the 30 gigabytes that you need for the 100 million. It's an awful lot of extra work. And again, remember, this is a vastly simplified version. So now that Duke has been open sourced, I have great delight in putting him into Blender, and so I've made a little fat Duke here. Blender's a wonderful little product if you want to play with it. So Java really is the issue on this. Now Java's, the language itself is not the problem, it's just the way we use it. And it's the way we typically haphazardly, it was designed to abstract us away from the memory, it was designed to abstract us away from the network, from the disk, from all of these things. We don't need to worry about where the memory is or whether we freed it or dealloced it, etc. it's sort of nice in one way, and it helped us a lot, but when we get into big data and high performance, it's a huge hindrance. So these fat objects, I'd call this really a vendor's dream. If you imagine the company where Java came from was Sun, their objective before they were bought by Oracle, they didn't do a particularly good job of it, was to sell hardware, or tin as they call it. So of course it's in their interest to sell something that consumes and uses up unbelievably large amounts of memory. They're selling tin, disks, they're selling computers, CPUs, networks, the whole shebang. And of course, the more and more you use this, I mean, if they made each object take up 100 bytes, they'd sell even more. If they go from 48 bytes to 96 bytes, they've doubled it, they can sell double the hardware and up go their figures. Now, Oracle are a little bit better at selling these sort of things, but they still sell hardware, and it's not really in their interest to reduce this because it makes a huge difference. And we're talking not, again, 20, 30, 40, 50%, we're talking hundreds of percent. You've seen the common delimited file goes at 4 times, over 4 times, 400%. And we'll see that it's vastly bigger than that as we get into other areas. So this was really, when Java came out in 95, everybody got into the Java, and it really was a wonderful, exciting language. I came from the C, C++ realms, spent a good 10 years before programming in C and C++. Really enjoyed getting into Java, but it's sort of like giving drugs to drug addicts or cocktails to Alcoholics Anonymous. It's once you're on there, you're hooked, and you're in there now, and we're all using these various different languages. Now, if you think this is just Java, this is the JVM. It's not just Java. Anything in Scala, Groovy, etc., you have the same problem. You're putting all these things in, you're abstracting, you're forgetting about it. Now, your code works, it's fine. But for anybody that was around and programming in the late 80s, the 90s, if you take Moore's law, you wouldn't imagine how powerful these computers are compared with what we used to have. They're unbelievably powerful. These phones, the little iPhone is thousands of times more powerful than the computers that my boss used to have, when I started. But unfortunately, the way we use them has not really gone up with Moore's law. We've just got languages that have abstracted us, and we haven't really noticed it. So we're really not getting this sort of performance out of these things. So all this memory needs cleaning up. The same is true when we get to the in-memory caches. We're sitting using these in-memory caches. These have become very popular. A lot of these started around 2000 as Java really became sort of de facto, particularly in the banking world. The founders of Coherence started in 2000. GemFire obviously was an objects database from back in the 90s, in fact, but it wasn't into Java until the 2000s. And Hazelcast is sort of fairly new. Neo4j is new, etc. A lot of these others are quite recent. Gigaspace is about 99. All of these I've used and remember from their sort of founding days. But every single one of these is using the same Java mechanisms. Now, also, to get a slight lead on their competitors, every single one of these has also put in little optimizations where they've seen, they use reflection, they can see that certain things certain types of objects have been using, and they can actually improve on that. But this is also quite time consuming when you're reading or writing from the cache. It only goes so far in how it works. So we're talking, in some cases, maybe 200%, 300% improvement, but we can do better than that. Now, again, reminiscing, it's nice and quiet here. Now, you all remember that, I'm sure. When that first came out, the film, it was just at the time when they were starting to encode sound using pulse width modulation. If anybody remembers that. So we basically didn't have the A to D or D to A converters, so you basically changed the width of the pulse to get a sort of slightly different frequency or volume of sound out. That took up an entire floppy disk. So my bag today is full of 2, 3, or 2 terabyte drives, and I walk around with sort of 4 to 6 terabytes of all the stuff, mostly that are sort of data I collect from places and things that I stream when I go to hotels. But all of these bits now, what's happened is we've gone from, it's consumers driven this, and consumers driven this compression. And we've gone from putting in just that one MP3 that lasts, what's that, 5 seconds on an entire floppy disk, down to being able to walk around with a phone with 1080p movies on it. Now that sort of compression has been driven by the consumer, and this is the compression or compaction that we need in the Java world, which we currently don't have. So let's look at this, get into a little bit more code. If we take this comma delimited file and we code this up, this doesn't look unreasonable. We've got a long, we've got the ID, we've got dates, strings, big decimals. Why do we use big decimals? Well, it's in financial services, you always use big decimals because you really don't want to have the pain of rounding. If someone loses a penny after doing 100 million trades at a few $1 trillion, somebody's in for big trouble. I mean, they'll pay themselves a 10 million bonus, but if they lose a penny off the end of that, somebody's head rolls. Ironic, but that's what it is. So we use big decimals, but I've just used this as an example. Yes, we could use doubles if we were using some other sort of thing, but that's not unreasonable. So we bung that in. And if we deserialize this or serialize it, this is unbelievably inefficient. We get one object for the object trade itself, and then for each one of those, we get another object. Now, you can imagine you've got umpteen gigabytes of heap. Those objects have been allocated all over the place. And then you've got defragmentation, and then you've got the garbage collector that kicks in. Then you've got to manage all of that. And if you're serializing, deserializing this, every single one of those is creating yet another object. And every single one of those is somewhere between 24 and 48 bytes. It gets not just large in memory, but hugely inefficient. If the CPU has picked up one of these, and a CPU has 2 caches itself, 3 in some cases, if the CPU gets one of these, the data it actually needs is in memory, and it could be dotted all over the place. And so there's no efficiency you're getting out of your CPU. You're getting no mechanical sympathy at all in this sort of system. So Java's very, very inefficient for this. Again, it was designed that way. Now we could store the row, so we could store the raw data. This, in many cases, is quite a good optimization. It's much smaller. We now only have 70 bytes as opposed to 300 and something bytes. And also the serialization and deserialization is quite considerably faster. You get another advantage that you can debug it because you can see the text. It's raw text on. The disadvantage, however, is if we wanted to read row 3, the second currency in there, we've got to do quite a lot of code. We've got to now read all the way through, count all the commas until we get to the right number of commas, and then read the data out. And that's quite expensive. And a comma delimited file is just one example. If we were going to JSON or XML, we wanted to read out the data, it gets horribly expensive. You'd need a SAX or some other parser to read the data out. So while it's quite efficient, and it is something that's used a lot, it's very costly when it comes to retrieving the data. That's what I was saying before. So again, serialization, deserialization is much, much quicker. Now we could compact it, and this is one of the things I heard in Stuart's talk. Somebody was talking about, compression. Why don't we compress it? Well, again, it's very, very costly. Now, yes, there are some compression which is quicker and more efficient, but if you really want decent compression, it's quite costly. Compression also works best if you've got batches because you can do better optimization on batches. If you've got a small comma delimited file, you're not going to get very good compression out of it because the lookup tables are sort of half the size of the file in the first place. And you want to be able to read one line alone without having to read a batch of 100,000 of them just to decode it to get that one that you want. So it is an option. Also, if the data is relatively random or relatively well distributed, it's also not going to compress very well. Compression only works if your data is lossy. So what if we store it as binary? So let's explore this one. If we take that comma delimited file and we somehow encode it so we can put it as a byte array, we would get rid of a lot of, we'd have very, very simple serialization, deserialization. We could also bypass the serialization because it would be a lot, we'll explore that. And while we're retrieving the data, it's going to be far more efficient because we'd know exactly where it is. We wouldn't have to look for the commas as we go through. So let me put something to you. This, on the left-hand side, is the standard getter and setter for the trade date. And this is exactly how in fact, the code on the left was generated by IntelliJ. You just click on the variables and say generate getters and setters, and it very nicely does that for you. And that's exactly what you'd expect. Code on the right, however, is hand-coded. I've created a byte array, and I've written some little comments, and I've manually encoded the entire message. Now, there's only 9 fields in there. It's not particularly complicated. What I've done with the date, because we only need the date, we don't care about the time, it's just the date. So what I've done with the date is I've basically taken off the milliseconds by dividing the date by the number of milliseconds, and what's left is just 2 bytes. Still gives me 100 years of resolution, which is fine. Nobody was doing trades in the past, and nobody's currently doing trades 100 years from now, fortunately. Or nobody would care if we did. What that means is we can get that into 2 bytes. If we know a little bit more about the data that we're storing, we can also make other sort of efficiencies out of that. But it basically goes down now from 48 bytes for the dates down to 2. That's a pretty good improvement. And we can continue to do this. And of course, I can copy and paste that bit of code there for the other date. Just need to change the numbers, but it gets a little bit more efficient. What's also interesting, and I should point this out, and I will keep pointing it out, it's the same API. Again, if we go back, the API is identical. And you'll see the overrides on the top there. I created an interface. So I've got 2 different versions of this. I've got the binary version and the object version. I've created an interface. And if I'm getting the date, now if I want a Java date, I've still got to create the date on the right-hand side. So it is still slightly expensive because I'm still creating the object, but I don't change the API. If I now change all my code to use these 2 bytes or to be more efficient and use an int, for example, then I can even get rid of creating the date for the return. But it does mean that storage is much more simple. So the API is identical. It means we don't need to change any of our code. So it's a huge advantage. What I'm going to do is show you through a little bit of code. If we can get this going. One of the disadvantages with screen sharing is that the resolution is so small I don't get any space to see what I'm doing. Let's give it a go. Mirrored displays. You can see that, it's good. Don't want to lose the presentation because that won't be very good. There's the spring stuff. Let's just get rid of that. There's the interest rate swap stuff. And here's the test trades. Here we go. Right. Now, what I've done, this is basically working on the interface. I was watching Stuart's presentation earlier, and I've realized that it's very hard to see the screen's not particularly bright. So let me just increase that in size a little bit. So basically, I've got a little thing. I create some trades. They're randomized, but they're quite cleverly randomized. I've put in some Gaussian distribution. I've made sure the days don't fall on weekends. I've done some sort of clever bits. So they look fairly realistic. I've rounded up the amounts, and I've put some little bits and pieces in. So basically, I create some trades. I actually create 5 million of these trades. And I'm using Java 8 to do that. So I create the trades, run a simple query. Let me show you what the simple query looks like. Yeah, I'm using Java 8 to do this. Hopefully you can still see that. So basically, simple query. All I'm doing is, as you go through this, set a little timer. I run through this 3 times because the JIT compiler is usually better to get it running first, and I just use the timing from the last one. It's quite a good little technique. If you run it once, you'll find it's the first 10,000, if you're using minus server as an option, will take actually quite a lot. The first one actually takes a huge amount of time, and then it speeds up very quickly. So it's often better to run through this multiple times. So I run through this 5 times. I use a Java 8, some lambdas here. So I'm basically doing a filter where the currency is equal to GBP, it's Great British Pound, soon to perhaps to be minus Scotland, good riddance, with USD. And oh, it's been videoed. Sorry, we love Scotland. Some of my best friends are Scottish. It's very, very simple. All I'm doing is getting one of those results out and then just printing it out. So it's nice and simple. It's just a little thing to sort of test it out. So we nip back up to the top again. we test the serialization. Now, the serialization's interesting. I started this by serializing it to disk. Now I've got SSD on here naturally, and I thought it's a little bit unfair because the disk is probably going to take quite a bit of time, and then there's dozens of different ways of writing serialization to disk, and most of the serialization we're going to be doing is across the network. So I thought disk is unfair. So what I do is basically I use a byte array. So I've got serialize and deserialize, as you can see here, just basically using a byte array output stream. All that does is serialize the object, returns a byte array, and the other one takes a byte array and takes it back. And so when I do the serialization, all I'm basically doing is serializing it across these byte arrays and testing it. So the timing I'm getting, what I'm doing is running through the 5 million, picking up the results and trying it out. So anyway, let me give you some results at the bottom. Now, this does take a bit of time to run, so what I'm going to do is I've cut and paste the output here, and I'm going to show you that rather than run it, because you see here it says 200 seconds, so we're not going to sit and watch that. So this is the object version. Now the object version is what you saw earlier. This is standard objects. So it creates 5 million of these objects, runs the filter, prints out 3 results. So it's basically just looking for picking out the GBP USD trades, then doing a quick sort on them. And the query time, 1.6 seconds. That's 1.6 seconds to go through. Now this is again Java 8, single thread. I'm not using parallel at all here. It takes 1.6 seconds to go through 5 million trades. It's nice and quick. Serialization, deserialization for 5 million records takes 200 seconds. I was quite shocked by that. That's pretty slow. And again, that's straight into memory. So not even hitting the disk at all. So there's no inefficiencies on the disk or the network packets. Serialized size is 668 bytes. Why is it much bigger? Because if you ever look at the what serialization does, it actually prints out the name inside, so you get all of the package names. If you want to shorten your serialization, then change your packages to A.B.C, etc. Silly things like that. I did a little check, obviously, to make sure what went in was the same as what came out. Now, binary version, this was interesting. So 5 million trades again. I was actually surprised it was slightly quicker. In practice, it's slightly slower because the objects are fairly efficient. Obviously, they're in the format that needs to be used. But this particular one was quicker. Now again, in practice, when we get into XML and more complex objects, you actually have to do quite a bit of calculation to work out where the data is that you want. So don't read too much into this. This is just a test, a sort of code that I wrote so that you guys can walk away with it as opposed to getting into too much complexity. Now the serialization, deserialization took 20 seconds. That's an improvement of 10 times. 10 times on top. It's quite considerable. And the actual size of this was 85 bytes. Why 85? Well, the actual object itself is 39 bytes. That's typically rounded up to the nearest sort of 8. And then, of course, we've got the name put in there, which is obviously what the package name that I put in. So it's 85 bytes. I also did another little test, and I used Java NIO. Now, because each one is a byte array, the byte array is 39 bytes. I rounded that up to 40 or 48 bytes, I can't remember. And I wrote 48 bytes into a byte buffer, and then I did Java NIO, and I zapped the byte buffer onto disk. And I did that for half megabyte chunks. And it took 0.5 seconds to write 5 million to disk. This is to SSD. And it took 0.2 seconds to read 5 million back. That's serializing 5 million in 0.2 seconds, compared with what standard Java took 200 seconds. So I think you'll agree that's a relatively good improvement in performance. So from 200 seconds down to 0.2 seconds. So where I'm going with this is the technology that we were using in Pivotal's RTI platform, which was being talked about a little earlier. So let me just go back to my slides if I can find them. Let's take off the share. There we go, that's the one I want. Turn off mirroring. Good, we're back. So let me show you some of those results. So looking at the bytes used on the classic Java version, the bytes used on the binary version, I think you'll agree there's a reasonably good improvement in performance. Now this is just, or sort of in memory use, we haven't got to performance yet. We're certainly looking at high hundreds to thousands. This is a really simple use case. When we get into the more complex use cases, we're seeing even better performance on this sort of thing. Now the binary data that was coming in from the telcos has about, I don't know, a good part of 200 variables in it. So it's somewhere between 50 and 200 variables in it. And those are recurring. You've got all sorts of different things, some of which can be not there or null. Others are recurring. You've got multiple instances of all the different cell towers each connection can see. All sorts of different information which has varying lengths. So you've got run length encoding and all sorts of things in there. So it does get a little bit more complicated. And there you really start to see some very, very significant performance or improvements in storage. Now the custom serialization is what I said before, is I basically rounded this up from 39 to 40 and then wrote this customized serialization. Now let's look at the performance on this. Time to query, don't read too much into this. Typically the binary is slightly slower, but what's important is it's around the same ballpark. We're not losing anything, and in this particular case it's actually faster. Time to serialize this, again, this is just pure serialization. This is using standard Java serialization. We go from, we get pretty much a tenfold or an order of magnitude performance gain on that. But if we put in the customized version, we literally get a 1,000-fold increase in performance. So we go from 400 microseconds down to 44 nanoseconds. And that's hugely significant when you're getting your data off the network. You're getting data off the network in batches. You're putting this into using Java NIO to basically process this. The reason we get that, and it's not only this, is the reason, another thing we can do is as we take the data off the network, it's already parsed. It's in the format that we want to query it. So we don't need to convert it from this byte array into something else. So when we query it, we're not searching through the commas or anything like that. So this is data we can use immediately. So that's just explaining the fact that we can now read this sort of 40 megabytes, which is a million of these trades. We can read it basically in one go, or we can read it in batches of maybe just 4 megabytes or something. So we can vastly reduce the amount of memory we need to process the same amount of data. So we can look at this in multiple ways. We're getting huge increases in performance. We're getting vast reductions in the amount of memory we use, but we're also getting huge reductions in the amount of resources that we need to process this. And if you can do that, you use less resources, you're using less machines, using less network. It doesn't make the people selling you the hardware very happy, but it does make the customers happy because we get an awful lot more. And if your garbage collection is not kicking in every well, a few milliseconds technically and taking up a large amount of time, then you're also going to get better performance results. So we're getting some other things we can do out of this. We can also create some objects. It's called these batching objects, and Stuart mentioned this. Now, sometimes your data comes in batches, or sometimes you can treat it in batches. You can still do batching and treat it as real time. Don't forget, with this RTI platform, we were talking of an average of 100,000 a second. So when we're talking about batching, we could batch 10,000 of those, and that's still a tenth of a second. So it's the network latency getting from the cell towers down to the systems we're processing is far in excess of that. So when we're talking about real time, we're talking seconds. So we've got plenty of time. We can batch these things up quite considerably. When we batch them, again, we have to stop thinking about the wonderful language of Java and putting things into lists, into arrays, into array lists and sets and things. They're wonderful. They're really, really nice. But unfortunately, each one of them takes up massive amounts of memory. And so we can actually create customized objects where if we put 1 million messages of 39 bytes, it should take up exactly 39 million bytes. That's the sort of thing we're talking about. Not something, when you bung it into a list or an array, it's all very efficient when you're talking about, or not efficient, it's all, the code looks nice. When you're talking about 1,000 items, it's fine, but when you start to get up to these sort of limits, I could not run that test with the objects at 10 million on this laptop unless I stepped it up to about, I've got 16 gig of RAM on here. I couldn't run it on the laptop. Whereas with the binary one, I can hit 100 million without a problem. So there's also some other things that we need to, again, this is going back 20 years for those of you that were programming in those times, and for those of you that aren't, you need to understand how your disk works. When you write a file to disk, it doesn't take up exactly that amount. Disk for efficiency, whether it's SSD or hard disks, uses certain chunk sizes. Your network uses certain chunk sizes called an MTU. And anybody that's been used to tuning these things has to tune the network packets all the way along your network. It makes a massive difference. If you change some of those sizes, you can see 2 to 3 times in performance impacts or gains. And it's absolutely vital at this sort of level to have to start getting to this sort of level of understanding of your hardware. If you were taking that comma delimited file, let's step it back up to the XML. The XML, the actual file itself is 7.4. This is averaging 7.4K. Once we've Java bounded, it's somewhere between 20 and 25K. So when we send that across, whether it's serialized or whether we keep it as XML, we send that across the network. We have to use several MTUs or network packets to get it from A to B. That's very, very expensive because they all have to arrive in order because we need to reconstruct this thing at the other end. So if you're doing caching, or if you're doing a big data network and your cache by definition, well, almost by definition, is spread across multiple machines, that's going to be hugely expensive. If we can now get this down to a binary array, which is about 400 bytes, that goes across the network unbelievably more efficiently than the 25K. So quickly looking at some of the utilization, I use a little tool from jClarity called Sensum. It's pretty neat. It does a sort of a post-mortem. All you need to do is put a few parameters, standard Sun/Oracle parameters, and it basically does a sort of post-mortem on your usage. Now, when we run this through the object version, the little tiny step on the left-hand side is the very first creation. So this is when we create the 5 million. So as you can see, it's going up, and it uses just over a gigabyte. Now, for those of you that can't see, scale on the left goes up to 8.5 gig. So it says 8,500 megabytes. So each one is 500, each step is 500 meg. So we hit just over 1 gigabyte on that. And then the long, slow climb, that's serializing. We're serializing 5 million and basically creating a second list of 5 million. And that's the 200 seconds it took to do that. And so, of course, when we get to the end, the roughly, what is it, 3.5 gig or so, that's the 2 objects in there. If we look at the GC pause time in that, the worst peaks we get are about half a second during the first bit as we create those. And then we can see that as we're basically climbing up, doing the serialization, even when you're serializing. So when you look at the code, there's virtually nothing being executed. You're putting stuff onto the network. The deserialization is going to create huge amounts of objects. And this is the garbage collection. Now, that line is sort of averaging out at about 150 milliseconds, or 0.15 of a second. That's quite a lot. There's a lot of time spent in garbage collection and that. And I've got it's an 8 gig heap in that particular one, but you can see it's using up quite a bit. Let's go, of course, to the binary version. Now, the binary version, you can't really see the difference in the 2 slopes, but it sort of ends at about, same at about halfway. It ends, the tiny little flat bit where you've got a few dots closer together, that's where it's doing the query, because it flattens out. There's no extra memory created during the query. That might change as well because it's Java 8, so we're not saying don't create any memory, it's just not in this particular case. We'll see it's much, much flatter. Again, the garbage collection pause times, the peaks at the top of this are 150 milliseconds, so 1.15 of a second. So that's the top of the graph. The previous one was half a second. So we can see this is quite considerably lower. Now I did the same one with the binary with a 2 gig heap. Why? Well, because in fact we're using less memory, so why do we need to allocate more? Things, to a certain extent, again, I'm sure you've been on courses about tuning your parameters for garbage collection and things, but just creating a bigger heap doesn't necessarily make things go faster. It just means that you wait longer until you have a nasty pause, and the pause is longer. But you get a little bit better resolution on this. This is exactly the same amount of memory usage. You can see it goes up in the allocation. During the query, it flattens out, and then it goes up again during the serialization. Now, this is the GC pause time, and because we've got less memory, it takes less time. So the absolute top of this is 0.045 of a second, so 45 milliseconds. So now we can start to see we get much, much better garbage collection or optimization of garbage collections. This is exactly the same. If we compare these two now, this is on the left-hand side, we've got an 8 gig heap. On the right-hand side, we've got a 2 gig heap. You can see the proportions are roughly the same. And again, garbage collection, just to give you the size on this, the graph on the right, the very top line of the graph on the right, is just slightly lower than the very first rung of the graph on the left. That's the sort of difference in scales on this, so a huge increase in performance. Now the code in this is really, we're talking just a few lines of code, so it's not that much of a difference. So huge difference in performance, huge difference in memory usage, just for a slight change in the way that you handle your code. So how do we take this beyond comma delimited files? Comma delimited files, okay, we've got a few different variables. We've got strings, we've got dates, we've got longs, ints, floats, doubles, a few things like that. But when we get into XML, if you've ever looked at, I'm sure you've looked at the standards, but there's a horrible list of different types of variables in there. So it gets pretty complicated. When we were working on the Telco models, they weren't using XML naturally, because otherwise our phones wouldn't work at all. They're obviously using binary, so we had to respect and implement all of the binary formats and standards that they had as well. But when we get into Spring, one of the advantages of actually having the same API that I was mentioning before is that absolutely nothing changes. So when we're putting things through our Spring integration workflow, there's absolutely no change to the code we've got at all. So this is really an optimization to the objects that you're putting through, but there is no change to the way this works in Spring. One of the very first things we came across, this was well over a year ago now, because I presented this, I think the sort of initial ideas on this about 18 months ago at one of the Spring shows, was the queries. So naturally we were reading in these messages super fast now, putting them into a Spring integration workflow. And we were using Spring integration to do the filtering and not the version that you saw with the Java 8 there. And the very first thing we came across was the SPEL time. Now there's been some quite phenomenal improvements in the performance of Spring integration now with this compilation of SPEL queries. And this was sort of after sort of conversations and ideas, sitting down with Andy Clement and Adrian Collier, basically, as usual, over a few beers, sort of talking about some ideas. But the cost of these queries now has gone down from about 1.5 microseconds to 60 nanoseconds. Again, this is just average. Things change. But imagine if you're doing 1 million messages a second. Now, 1 million messages a second, that means each one must take a microsecond. So when your query actually takes more than a microsecond, there's no way you're going to get 1 million a second. Now you've got to read the data, you've got to parse it, you've got to do some other, moving it from A to B, you've got to do quite a few bits, and then you've got to query it, and then you've got to send it somewhere else. What that means is all these different steps, you have to do the entire lot in less than 1 microsecond. So seeing something like 60 nanoseconds and seeing the fact that we can read it from disk in 40 nanoseconds, etc., we're right in the right ballpark, because we've got plenty of time to do lots of these things and still get the performance we need for 1 million a second. Why 1 million? Well, for the RTI, for the telco platforms, the average they gave us was, or the average we get is 88,000 a second, 24 by 7. 7 days a week, 365 days a year. It goes a little bit quieter at some times of the night, but you get one small event or whatever it may be, somebody dying, a terrorist attack, something interesting happening on the news, or anything, Christmas, things like that. The messages peak sometimes for half an hour, sometimes for an hour at 10 times that. So you're hitting 800,000 a second for maybe half an hour or more. Now, do the maths on that. There are a few hundred bytes each. Multiply that by, let's say, 800,000. Multiply that by 1,800 for 30 minutes, and that's one heck of a lot of RAM that you need to store those in a queue. We're talking many tens of terabytes. So it's not something we need to be able to process it at that speed. There are also laws which now say in certain countries, and I believe it's the same here, any of the telco providers must be able to provide information on certain users within a certain amount of time for anti-terrorism laws. Now, if your stuff's sitting in a queue and has been there for the last 20 minutes because you can only process 100,000 a second, it's not going to be very helpful. So we have to process at real time. So we have to be able to process without queuing at about 1 million a second. And those peaks for a few seconds hit 100 times that. So they'll hit 10 million a second coming through. So that's why we need to process these things. So this is critical. So the SPEL compilation has been an absolute massive change for us. It came out in spring 4.1. Naturally, we had early versions of this well over a year ago, and we've been, well, it's in production. So it's been well used and put into practice, and it's made a massive difference. What this means, we can now have the full Spring flow from end to end without that being the bottleneck. The bottleneck moves around. As you make improvements in one part, obviously the bottleneck moves to another part, and it's just one of these things you discover as you go through. Now, what we also used was code generation. Now, the very first version of the one that I demoed to you with the byte, should we say, binary trade, I wrote myself. It took me an hour or two because it was a demo. I wanted to be able to give you something, some code that we could demo, you could take away, and you can see how simple it is. Code generators naturally generate more, I wouldn't say it's obfuscated, but it's not quite so easy to understand because the goal is to make it work, not to make it readable. My goal was to make it sort of readable for you. The very first versions of the codecs that were used for the telcos were generated by hand, and I think it's a reasonable estimate that it took about a man-year to do the first couple of codecs. That was by a chap called Vinesh, who's an absolute genius, who coded these things, and it was that realization that this is the way that we want to do it. This is the only way we'll get the performance out of it, but it's also not the way to do it, i.e. hand-coding binary messages. So that's when they came to us, and that's where we generated. What we did was to take a standard Java binding tool based on Caster that basically bounds. All it did was look through the model, XML or any other model you've got. It would look through that, and typically it would generate the object-style code with the getters and setters, all the usual other utilities, and we completely rewrote that so it generated binary. So, I mean, I'll walk through these very quickly. We can basically, as you can see from here, we can import any one of these different types of standards. This is the time-saving part. So I could point at that comma delimited file and I could generate the code rather than the 2 hours it took me to hand code it. That's 2 hours while I was watching Apple's release yesterday, so I was being extremely inefficient and totally distracted on Apple Watches. But this changes it down to literally a few seconds. In under a minute, I could have the code. We can mess around with the model. So here's, again, this is the trade. We've got the header. As you can see, the header is optional. So we have 1 or 0 or 1 of these. We have many trades. We can click on one of those things. We can go into further details. So if you can see on the right-hand side, we can go into details of setting, is it a comma that's at the beginning? Do we strip out white spaces? Do we strip out quotes? Do we, how many decimal places does it have? We could even put in, we can change the customization of the binary that it generates. So there's a lot of information we can go in there. And so it's basically like JAX-B, but we've put a GUI on top of it. And then finally, all we do is once we've got the model, you can see the model on the top there, the top of the 2 blue bits, we simply click on that, right-click and say deploy, and that literally just generates the code out of that. And the code that comes out is not dissimilar from the previous one that I used in the demo. In fact, I redid the demo using this code, and I thought I'd just put it up for interest. It actually takes 33 bytes instead of 39. One of the reasons for that is we use run length encoding. Now, for the first ID, as Stuart said, we very quickly run out of ints because it only goes up to 16 million, and 16 million we hit very, very quickly. So we need longs, and again, even those can run out. But longs are 8 bytes. 8 bytes is very inefficient for the comma delimited file I was using. So we can use some clever bits where we use 1 byte in every case, and the way we encode the top bit of that byte defines on how many bits are coming out for the rest. We can do the same with strings. We can do references to strings, so we can build up commonly used strings and refer to those, and then we can have a special case that if it's a different string that's not in our common lookup table, this is the same way that compression works, it builds up a table. If it's not in there, we can basically override it and put in the string. What this means is the actual length of our binary changes. So on average, it was 33 bytes. But as we got up to larger numbers, it would start to increase, maybe 37, 38 bytes, etc. And then different things would change it. So each one of those changes very, very slightly. So it's what we call run length encoding. So going back to the big data side of this, what we're able to do with this is basically take the data coming in binary. Now, in this particular case, for the telcos, the data was already in binary, so we didn't need to create it in binary. But we were able to use exactly the same concept. So we generated the models all the way through the multiple systems. Again, as you probably saw from Stuart's slides, we got 2 caches, GemFire caches. We're using Spring integration workflows through the entire system. Comes in from a reactive framework straight into the first cache. There's some sorting and real-time intelligence done inside that, and it goes on to the second cache. What we need to do is take out some of the IDs of the fields for the analytics, because under certain laws, obviously, you can't identify the people, so we have to do some anonymization before it goes on to analytics, etc. So again, there's quite a bit of processing needs to be done, but this is done in real time. So this is, I think I covered that bit. We basically mapped the 2G, 3G, and 4G. 4G is like LTE here. We're looking at about 100,000 a second on average. Again, all the different technologies used there. A reactive framework was very key in this. Netty, the sockets, GemFire in this particular case, and obviously Spring XD. This was, out of interest, the telco model. This is just a sort of just a snippet to give you an idea of what it looks like. And of course, each telco model is sort of based roughly one another. So as they move from 1 to 2 to 3 to 4Gs, etc., they basically add new bits. Obviously, you've got the geo encoding and various bits, but it's quite often the case that you can take one and make modifications as you go up. And as you go from country to country, they have slight different modifications, and one provider to another. I want to go through a little, just a couple of slides here to give you a little bit of sort of an idea of the sort of thing we can do. Now this is from some of the internal or sort of pivotal slides that are used on this. We can map the networks in real time. It's absolutely critical now to be able to discover what's going on in the networks, discover where there are problems with the network, where the networks are shutting things off. We can do this in real time, not just by seeing the entire map, but we can also take it down to the phone type. You find people phoning up saying, I'm having problems with my phone, and then you get lots of those, and you can say, oh, it's everybody with an Apple phone or a Google phone or something. You can actually see, you can work out whether these problems are maybe down to the network, maybe they're down to the cell providers or the phone providers, etc. All of the information is there, and it's just like it's working off a database, but it's in real time. And again, we can query the GemFire database or whatever mechanism has been used under this, and basically extract the information in real time. This particular one is graphed, and these are the sorts of things that can sit up and run in the offices themselves. Now this is a little video I just wanted to show you. It's only about 30 seconds long. This was a demo that was done at a trade show, a mobile trade show. This is sort of one of these ones, global ones, where people came from every country in Barcelona. For those of you from Texas, Barcelona's actually in Spain. Spain's a different country. It's not in America. I was going to show you a map, but I thought you probably wouldn't get that either. Now what this shows is certain people opted in, and we can actually show a heat map of where the phones are. Now, you're probably not aware that in a lot of these days you have micro transmitters or cell towers inside shops, shopping malls, etc. Well, I don't know what that was. That's interesting. This is the conference. It's on the sort of top right, and you can see people who have opted in for this. This was just people who opted in for the conference. And you can basically see as they move around, you could watch them traveling in to the conference, etc. And this was running live in the conference in Barcelona. And all of this, and although this is obviously recorded, there's very little point in running it live when somebody turns up at the stand at a time when nobody's actually doing any traveling. So they basically record this, on the first day and then show it over and over again. But these are the sorts of things you can actually do live. I had a little bit of fun myself. I was working on there's one in Turkey. Now, I wouldn't expect anybody to recognize what this is a map of. This is just the small peninsula of Istanbul. From here upwards is Europe. This on the blue bit on the bottom is the Bosphorus, and which you can't see just to the bottom right is technically Asia. So this is where you can get boats backwards and forwards between Asia and Europe. So this is Istanbul, which is an absolutely massive city. Now on the left, you can actually see a driver, somebody on a bus, but somebody certainly traveling at a reasonable pace. We can actually track individual people sort of moving around. And basically, we don't know who they are naturally. We can tell you what phone they're using. We could tell you all sorts of information about the URLs they're watching, all sorts of interesting stuff. But this is sort of data that we're busy processing. On the right-hand side, that's just a 10-minute interval. Processed 21 million events. It took about 3-4 minutes to process that. It did about 137,000 a second. Again, all binary, and I did that in one thread on my laptop. So it's not even multi-threaded. So it sort of gives you the sort of performance we can get out of this now. Oh, it's sort of slightly bigger. So you can just sort of see the little blue dots. Not very exciting. This is my own code. I was, I wrote this on a plane, and I downloaded the Google Map API to be able to plot stuff on Google Maps. Sadly, most planes, well, probably a good idea at the moment, but most planes don't have Wi-Fi on them, so this particular one didn't. And of course, the Google Map API doesn't work if you can't get hold of Google. So I downloaded OpenStreetMap. So I got a whole bunch of OpenStreetMap maps, and I could basically plot these. So that's what I was using. So the entire thing I wrote on an aeroplane. So this sort of thing, again, this isn't the pivotal bits. This is using the same framework, full Spring framework, just basically plotting results. And it's the sort of thing that the analysts and things sit down and, how can we get some interesting data out? Can we find people that are having problems? Can we find people that are, calling up issues with data? Can we group people into different companies and provide them different network plans because they're doing different things? If it was AT&T, how do we cut people off faster? So these are some of the key points that I want to sort of push out. If you're pushing the bounds of performance, both in scalability, performance, memory usage, etc., you should really, I believe, think about refactoring some of your code and refactor just the way that some of it works. You don't even need to do all of it. You could just do a little bit of it. You could take that object that I had and you could just take out a few of those things. Put some analyzers on it. Put the JVisual VM or the new one now, I've forgotten the name, the Oracle gadget, and you can analyze your code and just look at where the memory is going, look at where the CPU has been used, and just take out a few of those little bits. You'd be amazed. Just a small, you saw just a tiny little bit of code that I wrote just for that date, for example. Write some good tests for it, make sure you've covered the way it works, etc. But it makes a huge difference. As you can see, we're not talking 20%, we're talking several 100%. So these are all things that programmers, if you went for a programming interview in the 90s, those are all the things that you had to know about. How much, how big is an int? And which is faster, A++ or ++A? There's actually a difference between the two in those days. You don't know that these days in Java because it's all abstracted, but it used to make a difference. Spring 4.1 has some massive performance improvements. So again, seriously look towards moving to Spring 4.1 for some of your code. Again, if you're pushing the edges, you should be keeping up with it anyway. Alternatively, just go out and buy bigger, faster machines and make all the hardware vendors really happy. Sure, they'll take you out for nice meals and look after you nicely. I finished. I've got about, I think, some time left for any questions at all. Mark.
Have you ever tried with some of the alternative serializers, not the raw JDK one, like there's Cryo is one, there's a GitHub page of performance of Java serializers?
So a question about,
Cryo is one.
Yeah, did we look at any different serializers and things? Yes, over the years, I mean, we've looked at, there's layers, we looked at protobuf, we looked at all sorts of different things. I think the difference, the advantage we had was because we model the code, a lot of these other things were based on the instance data, and they didn't have knowledge of the model that created the instance data. So it's a bit like seeing a currency come through as 3 letters and not knowing that in fact it's only one of 163 different currencies. So when you look at the model, you can actually make a lot more assumptions, a lot more intelligence out of it. There were things like you'll see a month and you'll know there's only 12 months in the year, so you can optimize that and store it in just 4 bits. Whereas if one of these serializers just saw a number, it wouldn't know that it could potentially hit, it could be an int, so they can't make these sort of optimizations. So what we've done in the GUI is allow someone to go through and annotate effectively the model. So you see the model and say, in fact, we know this is not going to go above a certain amount, or we know this is only going to have X values, and so we can create an enumeration out of this. So far, we've pretty much blown all of the others out of the water in terms of what we can get out. When we sent this to some, we did a white paper on gigaspaces, GemFire, and coherence, and we basically showed the performance improvements, and it sent them off to the founders, CTOs, and guys that we know on these things, and you get back an email a few weeks later because, sorry, been busy, blah, 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 looked at this, sent it off to my engineering team, and they don't believe it, can you send us some code? So you send them some code, and then you get a reply back about 2 days later. It's like, holy shit, how did you get that working? And it's quite an amazing difference. Yeah, question.
So consider there is an application that's built on Spring 3. So migrating the application from Spring 3 to Spring 4.1, will there be any kind of potential improvements? Because your last slide says that migrate to 4.1. So if there is any kind of improvements, will there be the improvements in performance or without migrating the actual code to use the binary stuff?
That's really a question I would throw down to one of these guys sitting at the front here. So the question was about the difference in the profiles between moving from Spring 3 to 4.1. Do any of you guys want to jump?
I think your slide was talking about this particular SPEL compiler. Right?
Yeah.
But
the SPEL compiler will just kick in on its own. I mean, it's behind the scenes. There's configurations to make it immediate, to make it kick in after a certain amount of iterations, a bit like the JIT does, or to turn it off altogether.
The other thing I would say is that it's unlikely that the framework is going to speed up your application if your application itself is
Oh, very good point, yeah. I mean,
it's unusual for the framework.
Yeah, I mean, most performance improvements are down to the architecture and the overall architecture of your application. That moving from 3 to 4.1 is unlikely to make the difference. If you've got SPEL compilation, for example, if you're still using classic Java objects, you probably wouldn't even notice it. It's, you know, these are performance enhancements and tuning when you write down at the edge that you'll start to notice at that point. Again, if I was to stick it in on those big Java objects, again, you probably hardly notice because it's spending too much time messing around with creating objects and garbage collection. Any more questions? Is that... Sorry? Does it handle internationalization? Yeah, I think it, well, I know it does. There's always the odd country that you can't get, but one of our biggest clients is in Japan, and we put a lot of stuff through the Jazz Deck and Bank of Japan. So we've got a lot of internationalization. Certainly, if I go back to the other slide, there is a part in there for internationalization for setting up different profiles. So yeah, definitely. As it took Sun umpteen years to cover internationalization, I mean, being a Brit, as you can probably tell from the accent, we're a little bit more used to different languages and sort of having to put up with French and German and bits. We don't put up with them, we like them, but I mean, having to sort of cope with different languages, shall we say. And as you saw, part of that was part of it was Spain, Turkey, UK. Now they've still got this, roughly the same alphabet, but Japan's certainly a different alphabet. We've managed that fine. Any more questions? No? Okay, thank you very much.